Welcome back. Thanks for coming. Going to talk to you about vapor cloud risk management. Now, this one is one that could be applicable to the chemical manufacturing industry, the oil and gas, the power or utility industry, specifically in transmission and distribution. And it's an interesting subject. The background is that I used to be responsible for LNG operations and LPG operations in a risk management capacity. I wasn't an operator, but I had to help teach the operators how to control vapor clouds. One of the plant managers came to me one day and said, can you help us understand how to control vapor clouds? And I said, well, on one condition, and that's that you never try to do it. So I went ahead and prepared a training program with the understanding that the guys were going to see vapor cloud ignitions and explosions and fires. They were going to learn all about how to manage them, but that they were not actually physically without proper PPE, that is turnout gear and SCBA, or at least turnout gear if they're exterior advanced firefighting. So he agreed, and we put the program together, and hopefully you guys can get some value out of it. So let's talk about a LNG spill. Here you go. This is real liquefied natural gas. It's on the ground. That's why it's boiling. It comes out about 270 below zero, and the ground's about 70 Fahrenheit. So 300 degrees of Fahrenheit gets it boiling. You notice that vapor cloud is laying on the ground. That LNG is still 50 below or colder. As it warms up, it tries to rise, but you can see that it really doesn't burn that fast. The flame front is so slow that you can actually walk through it. So now, let's talk about what we do about a vapor cloud. How are we going to control the formation of that cloud? How do we reduce the size of that cloud? When that cloud's going somewhere we don't want it to go, how do we control it? And finally, how do we keep them from igniting? Let's prevent ignition of these clouds. Stick around to the end because you're going to find that maybe sometimes we'll light them off on purpose. All right. I was talking to the plant operators, and I imagine I'm talking to a lot of plant folks right now because that's who subscribes to my channel. Great to have all you here, and we're going to talk about you guys being the experts, right? If you're the plant manager or if you're the operator, when the fire department arrives to your site, you know more about your hazards than they do, right? So they're going to expect you guys to be experts. And, you can understand it. Your emergency may not be the first emergency that they've attended to that day, right? So just be considerate that these are general duty, all-purpose emergency responders. They're not necessarily LNG vapor cloud responders or propane vapor cloud responders. So they're going to look to you at the facilities as the experts. You people are going to be who they lean on for their security. So let's look like experts. All right. We're going to look like experts. First, let's talk about cooling. If we've got let's talk about a propane tank that's got some heat, maybe some radiant heat from a fire across the facility, and we're worried about the buildup of pressure. Well, if you take a tank from 100 degrees Fahrenheit to 75 degrees Fahrenheit, blowing water on it, you're really only dropping the pressure in there from 185 to like 130 psi. So you've still got quite a bit of pressure, and you've exhausted a lot of resources and a lot of water spraying on a tank that isn't really involved. So that's not one of the things that we would put as a top priority. Another thing you can do is heat the pool. So if you've got, and we'll talk about it later, it all depends on the product. If you think that you can make it buoyant by warming it up and creating the vapor, and that you can control that resultant vapor cloud, then you would do that. An example would be an LNG cloud, because again, when you make LNG warmer than 50 below zero, it becomes buoyant. So if we can get it warm, we can get it above the ignition sources. Most of the ignition sources are on the ground. So if we can get that vapor cloud up off the ground, we can get it away from the ignition sources. Give you a little tidbit. If you put high expansion foam on a propane liquid spill, you're going to double the length of the ground-based vapor cloud. If you put high expansion foam on a LNG spill, you're going to cut the vapor cloud length along the ground in half. okay, because it gets buoyant and it goes up. So that's what we want to do is get that LNG away from the ignition sources. Next, we will look at dilution. If you have a vapor cloud that's methanol, ethanol, acetone, some sort of water miscible product, then yeah, dilution may work. But you're going to need a lot of water. You're going to need 4 or 5 times the amount of fuel that's there. And be careful, because if the water is adding heat, you may actually increase the boil off in your attempt to dilute the product. And next, emulsification. It's out there in the literature. I don't see it being used except in maybe transformer systems, but the concept is that the water droplets break up the fuel and make bubbles that then retard the vaporization of that fuel. Alrighty, phase separation. Please write in the comments. I've never done this, didn't have to work with much alcohol or alcohol gasoline mixtures yet. So please let me know if you guys use phase separation and how it works out. But basically it causes the alcohol to sink and then the foam can do its job. All right, now controlling the vapor cloud formation, what we can do is, we talked about foam and additives, and with respect to most of the vapor clouds that we're going to have in industry, we haven't really found a foam that's applicable to put on before the ignition. After a pool ignites, high expansion foam's great on an LNG pool because it insulates the liquid pool from the fire, from the flame, the radiation coming back down from the flame, so that can reduce the boil off. It also forms a crust of liquid on top of that LNG pool that every now and then it cracks, and then you get a little burst of gas coming out. So it's a much slower release once you've put that high expansion foam and it's had a chance to freeze. Next, talk about sorption. If you have ammonia and you've got something that actually chemically reacts with water, if it has an affinity for water, you've got a chance to get it out of the air by spraying water into it, okay? It could work with chlorine, but produces hydrochloric acid. Next, scrubbing. Well, if you're not really chemically reacting, but you're physically knocking the cloud down, it can work on dusts and mists, okay? It doesn't really work on air vapor, and we'll tell you why, because actually all it really does is adds more air that you have to be careful about. So, water spray versus air entrainment. In a minute, we're going to talk about ventilation with water. And when you get more spray, you get less air, right? So we'll talk about why and what's going on, but really it depends, your choice of which you use depends on the type of release. So if you have a jet type release that's spraying very hard, then you would want a more straighter stream of water to push back against that jet. If, say, for instance, you had a spill that the only thing moving the cloud was the wind, well, then you could use ventilation to try and push back against the wind. Rather than a small, straighter stream that might just cut into the cloud, you want something that's big and broad and going to move that cloud. So we'll talk a little bit more about what ventilation options you have in firefighting with equipment that you've got. So when you spray water, the water droplets basically have friction in the air. And the friction in the air slows the water droplets down, but it also causes the air to move so that the energy, some of the energy is transferred to the air. If you have a whole lot of small droplets, you move a lot of air. If you have one big droplet, you only move a little bit of air. Okay, an 1.5 inch nozzle is going to move about 50 CFM per GPM. So keep that in mind. We'll do the rest of the math. I know you guys, you engineers, are all trying to figure out how many CFM you get out of a hose line. We'll get there. Next, all right, the spray angles are critical, right? So again, like I mentioned, that if you have a 30-degree cone, you're going to move a certain amount of air and you're going to get that reach that you want. But if you open it up to 90 degrees, you're going to get 5 times the amount of air. Great, but you have to be 30% closer. When you're talking about moving a vapor cloud, you want to be as far away from it as possible. In fact, we'll get to a demonstration what we do at the end. You're going to want to be probably 5 times the size of the cloud away from the cloud. Okay, that was the experience that I had from lighting hundreds of propane vapor clouds, that basically whatever size cloud we had on the ground. The cloud above was about 4 times bigger, so I'm just saying let's make it 5. It's easy to remember. 5 times the distance. So if you've got a 10-foot cloud, be 50 feet away. If you've got a 50-foot cloud, you better be a long way away. All right. Now, how much air can we move? The question gets answered. A standard 1.5-inch hose line moves 5,000 CFM. Okay, that's about the same as a 16-inch fire department smoke ejector. Think about that. No electricity, the water you're already carrying, the hose you already have, you can turn it into a big smoke ejector and move air. If you have 2.5-inch hose lines and you've got, the crew to do it, you can move 130,000 CFM. That's a lot of air. Okay. Now, the other thing you can do with water is you can create a barrier. And remember that, sometimes you're using the momentum of the water to push back against physically the momentum of the vapor cloud droplets or the vapor cloud constituent. Other times you're going to use small size air droplets to move a lot, or small water droplets to move a lot of air, to move a lot of that vapor. So, larger droplets move smaller volumes, fine droplets move large volumes, kind of back and forth. Now, what else can we do with this barrier? We can cut off the water. You can kind of see what the guys are doing. They're putting that water up and then having it fall in between the imagined fire on the left and then the structure on the right where they're trying to protect it. But basically, you're just trying to set up a curtain and be careful. The curtain will slightly prevent some damage, but this is not any kind of last resort. All right, now be real careful about ignition. When you're using water and you're moving air, air can build up static. And yes, that static can ignite the cloud rather than move it or control it. So it's a judgment thing. If the air is very dry, if you're already getting shocked, be very careful about how you apply that water up into that vapor cloud, because it could contribute to an ignition. All right, now, well, the other thing that when you start spraying water, if there is an ignition, remember you're adding air, you're adding wind, right? Fires grow on windy days. So just be aware that as you start to try and control this fire, you may add the ignition source, add the air, make it very hot, and before you know it, it's something that you weren't even ready to deal with. So don't start operations until you have plenty of your resources available to get everything down below the lower flammable limit. All right, to suppress the ignition sources, it's you can use water. So if there's a possible source out there, remember that even with an 1.5-inch hose line, 7.5 feet away, flowing 100 gallons a minute, 60-degree hand line, that's a lot of water, right? 1.8 gallons per minute per square foot. Our deluge systems are designed at 0.3 gallons per minute per square foot. Inside sprinkler systems are at 0.1, 0.2 gallons per minute per square foot. So 10 times as much water. And guess what? The ignition is still possible, but it's not likely, right? The ignition source is not likely to survive that. You couldn't really put a flare in that deluge of water and have it live. But if you had a hot piece of metal or a hot, existing source that wasn't going to get cooled, that could ignite it. It's just not likely. All right. Now, ignition suppression works by direct cooling and by ventilation. When we inert, what we're doing is we're basically making the cloud to where there's not a sufficient ratio of fuel and air together. We're going to put something in the way, and that water gets in the way of the fuel and air, and you need about 18% of it for it to be effective. Your droplet sizes have to be about 1 micron. That's small, because even what comes out of our deluge systems, that's 100 microns, right? And what's coming out of our hoses is even bigger than that. So keep that in mind, that you really have to have a fine mist to start thinking about inerting a cloud. And if you think steam's going to be better, think again, you need 27% more. Why do you need more steam than you need water? Well, if you think about spraying water droplets into a cloud, they still have the ability to take heat out of that cloud. When you start to vaporize that water droplet, it expands 1,700 times, and the latent heat of vaporization causes a decrease in temperature. Well, if you've already put the steam into the cloud, it can't expand, so it can't push out any more of the gas, and you're not going to get any latent heat of vaporization. So steam is not going to be as effective. You need more of it. And so basically you're not going to inert with hand lines. Another way to stop an ignition is quenching. And if you can think about a spark arrestor, the way it works is basically when the fuel and the oxygen react and start to give off heat, they send that heat to other fuel and oxygen so that they can join the party. And it's just a chain reaction. As we get another group coming in and it gives off heat and energy, it goes and starts this chain reaction. Well, a spark arrestor or a flame arrestor gets in between that, and it doesn't let the heat and energy from this dance over here allow anybody else to come into the party. So it basically blocks the door of that transfer. And it's been done in laboratories, but not successful out in the field. But now you know what it is. All right, what about intentional ignition? I told you to stick around. All you loyal folks who didn't click off after the intro, you're going to get the benefit of something that I don't think many others have put together. I'm pretty sure you probably haven't seen this before, but this is live propane vapor cloud intentional ignition training. And after one job, I got to work for another company who handled a lot of propane. And we found a regulation, that required that if we transmitted that much propane, we had to be prepared to handle large propane releases, including intentional ignition. That's in our federal regulations, that our employees had to have the ability to intentionally ignite vapor clouds. Well, you can imagine these folks don't even have turnout gear. They've got FR clothing on and hard hats, but they're not going to be using hose lines. They're not going to be making the cloud diluted. They're not going to do anything. Really, if they don't see the cloud start, we didn't want them igniting it. The idea was that they could only ignite clouds they saw start, and the reasons that they would ignite it would be that further down the valley would be a neighborhood or a community, and we didn't want to fill the neighborhood or that valley with propane, which could very easily happen in our large transmission system. So it would make more sense to go ahead and ignite it, have a torch fire, deal with a few burnt up trees, but not have several potential explosions and fatalities. So we had to teach our folks how to intentionally ignite this. Well, remember, I had ignited hundreds of vapor clouds, but not with flare guns. All of our flares were stationary on the ground. We saw all kinds of crazy things with the amount of propane that could roll over a flare, and it would not ignite the cloud. And you'll see one of the flares that goes in the middle of this cloud glowing, and it's not burning. The cloud doesn't ignite from that flare. So it was very eye-opening to learn just how sensitive propane is to ignition. And well, let's just show you the next one, because here it comes. The flares are on their way, and we taught them that actually everybody kind of learned that you needed to shoot the edge of the cloud. Notice the guys are standing behind the truck, and they're trying to be 5 times the distance away from that cloud. I guess perspective changes really how far away they were, but that was our suggestion, to be at least 5 times away. The distance, 5 times the cloud's distance or cloud size, is away. And you can see 2 flares. One's already in the cloud, one's on its way to the cloud. And that's the one I was saying, it did not ignite it. So once we got ignition, okay, this vapor cloud that was on the ground is now moving up, and this shot is a few milliseconds after, but initially that fireball was quite a bit bigger. And as the fireball goes up, as it becomes buoyant and all the air around it comes rushing in from what got consumed, it rises. And so we see this all the time, is a ground-based vapor cloud but a sky-based fireball. So just be aware of that a minute ago you were behind the truck, but now this big fireball is in the sky shining down on you. So just be careful about what you think is safe. All right, so we trained the folks to do that, and to my knowledge they've never had to do it in real life, and let's just keep it that way. So, general rules to control vapor clouds. Pre-plan your response. Know what you're going to do. You've got your own chemicals. It's not necessarily a big mix of everything that I covered today. Pre-plan it. Evacuate as necessary. Make sure that everybody gets out of there, because vapor clouds can explode if they've been sitting there for a long time, if they are heavier than air. you really have to be careful that they aren't just a big fuel air bomb, and your attempts to control or move or push it could ignite it. So be very careful. Evacuate everybody before you do anything. Control all sources of ignition. I can tell you the big vapor cloud that I talked about in a previous story that was 100 yards long and 10 feet deep. This vapor cloud, basically when the police showed up to the plant to control traffic, they started putting flares down on the ground. It's like, no, we don't control traffic. Just, stay away, please. Never enter a flammable vapor cloud, even if you're wearing turnout gear. Look, the vapors are going to go inside the gear. So if it ignites, that whole cloud, you're in that cloud is in your clothes. You're going to get flash burns underneath your clothes, and you can't take them off. Don't go into a toxic cloud, okay, without adequate PPE. Ventilate the clouds. Make sure you can get them down below flammable or down below toxic before you go in. And then make sure you have a dependable backup water supply and reserve lines for rescue if you need them. It's a complicated topic, and I'm glad that you guys stuck with me to the end. I hope you got something out of this, and hope you never have to deal with a uncontrolled vapor cloud in your plants. Thanks.